the talk will be given by Michael Schwartz from Graz University of Technology. And let's welcome our speaker.
So thanks for the introduction. Welcome everyone to this last talk of the last session. So I'll be talking about ConTExT, approach for mitigating Spectre, so it's not an attack this time. And we have seen that since 2018 with Spectre, with Meltdown, an entirely new class of attacks emerged. And we have seen then on like Foreshadow, the NDSS class of attacks, with Fallout, with Zombie Load, many attacks in this new field of transient execution attacks appeared, and everything looks broken and the world is burning, and we need to do something against that. So luckily, they're not all unrelated, so they are in the same class, but we can also classify them a bit more. So we have some root cause and transient execution, and on the one side, we have this exception type, meltdown type attacks, and we have a lot of them. So there are so many that you can't even read them anymore because it is so small. But all the red nodes you can see on the slide, that are meltdown variants that actually work on at least one CPU. And on the other side, we are talking about the class of Spectre attacks. So these attacks, they use speculation, they predict something, and we have this type of Spectre attacks. We also have a few of them. So at the beginning, we thought there will be more Spectre attacks than meltdown attacks. Turned out it's the other way around. But still, also all the red nodes that we can see here are Spectre attacks that have been shown to work on at least one CPU. So these are the two classes of attacks, and all the attacks we know so far fall into either the meltdown type or the Spectre type class. And the good thing is, for a meltdown type class, they are basically vulnerabilities in the CPU, and we can fix them. That might not be easy for CPU vendors to fix all of them, but we can also see that in new CPUs, they are all fixed. And we mitigate them, and this is fine. But then we have still the class of Spectre attacks remaining. And it's not that many, but still a lot of attacks. And they're also quite dangerous. And they're not really bugs. So the thing for Spectre is, we are talking about some speculation, some prediction. And we can have an abstract view on how that works. So we have some operation in our instruction stream. And at some point, we need to predict. That can be a conditional jump, where the CPU doesn't know whether to take it or not to take it, or an indirect jump, indirect call to continue at a different location. Or it could also be a data flow prediction. So where to take the data from the store buffer or from the memory. So we have some kind of prediction where the CPU at this point does not know what will happen next. And we have some dependent operation on that where we continue. And this is the part that is then transiently executed because the CPU doesn't know at this point whether this should actually be executed at some point or not. So it executes it. If it's wrong, then everything is just rolled back, discarded. And we have this transient execution here. And this is the thing where stuff can get wrong. Because in the meantime, we execute things, we can influence the microarchitectural state. We've also seen that in the first talk in this session. So yes, this is not a bug. So it's a feature, and speculation is a feature that we want to have and we want to keep because it gives us a lot of performance. Otherwise, the CPU has to wait there to figure out what it can do next. So we want this feature. It gives us a lot of performance. So we don't want to get rid of it. We could disable it in the hardware, but we want to actually have that feature. So still, we should do something. So what is the dangerous thing here? If we look at a really simple Spectre gadget, the Spectre Variant 1, it's basically a bounce check. We check whether X, our access to the array later on, is within the length of the array. Then we access this array at this position X and use the value we get, multiply it to spread it out, and access a different memory location based on the value we get from the access. So if we illustrate that, it could look something like that. I always like some illustrations. It's easier to understand usually than jumping directly into the code. So in this case here, we have this if condition, and it checks whether this index is smaller than the length of the array. And the CPU might speculate at this point because it does not know the exact value of x, which is 4. And it already fetches the value from the array. Array at position x is the key. It's out of bounds, something secret there. Takes that, uses that for a subsequent memory lookup in this Oracle memory, and accesses the K page here. And this is put in the cache. And when the speculation is over, everything is rolled back. We never see this value architecturally, but we can use our favorite side-channel attack to retrieve it from the cache and learn this secret byte that is out of bounds of the array. So this is a simple variant for Spectre 1. And if we look at that, if we compile that, look at the actual assembly code, then this is just this linear control flow here. We start with the bounds check here, compare the index to the length. Then we access speculatively, because we predicted out of bounds. We access some value we're not supposed to access. We have that secret, and then this red part here is where it leaks, because we do a secret-dependent memory access with a value we're not supposed to access, and encode that, in this case, in the cache. And then we continue. And we don't want to do that because that leaks our values. So what is the mitigation, state-of-the-art mitigation? We add a simple memory barrier here, an L-fence. And this is what Intel and AMD suggest, and ARM. So just after every condition where it could speculate, we add a fence, and the fence is designed to stop the speculation. So when we look at that in the instruction stream, we do this comparison, we do the bounds check. After that, it can't speculate anymore. It can't speculate on the outcome. It just stalls there. CPU stops. And this is good because then we can never reach this red part where we actually leak the value. But we also see we don't execute anything at all after that. So that gives us, of course, some performance overhead. And that's not negligible. So we have kind of a high performance overhead if we use this state-of-the-art mitigation. And this is only for Spectre Variant 1. But we have seen there are many, many other variants as well. So for the other variants, if you also apply all the mitigations, we have kind of a lot of overhead. And in addition to all the overhead, it's also super difficult to find all the branches because you might not even see them in the source code. The compiler can introduce something like that. So what we want to do, and that is the idea of ConTExT, we don't want to identify the branches anymore that can be misspeculated and leak the thing, but instead we go over to identify the secrets, because we know what things in the application we don't want to leak. These are our secrets. And if we identify the secrets, like our cryptographic keys, then we can annotate them in our source code and use a different memory type to store our secrets. For that, we introduce a new type of memory that's basically still in your DRAM. It's just marked with an entry in the page table that you cannot access this memory contents while you're running in speculative execution. And this is nice, because then you can still do all the things, but you have your secrets somewhere stored safe, and in the transient execution, in speculation, they cannot leave their space. So you just don't get the secrets in a dependent memory operation. You cannot retrieve them. And we also, if we implement that, it could look something like that. So we have an annotation, like array here is our secret as before, and we mark that as being not speculatable, that is stored in this non-transient memory where we can't get it out during speculative execution. And we don't have to do anything else. We don't have to identify the branches. And if we look at that in the execution stream, then we again have the bounds check. Then we have this speculative out-of-bounds access to the array, but it's marked as a secret, so it simply doesn't do that. We don't get any secrets in the register, and we can't leak anything because we don't have the secrets. And still, we continue with the remaining instructions that are not dependent, so we don't have this huge performance hit. Yes, a simple idea. For that, we of course need this type of memory where we can't access something in speculative execution. We need a simple form of hardware taint tracking to track the secrets in the registers, because if they're already in the register or in the cache, we also need to prevent them leaking from there. We need a bit of compiler support for the annotations and to ensure that the compiler does not spill anything on the cache, on the stack. And a bit of an operating system support for context switches and for annotating the things in the page table entries. And the good news is many of these things already kind of exist or can be done. And this is the implementation that we have, ConTExT Lite. It doesn't have the full security guarantees, but it still shows that it works. And instead of a completely new memory type, we use uncatchable memory, because uncatchable memory is documented as you cannot access the contents of uncatchable memory during transient execution, during speculation, because it might be memory mapped I/O. And if you would access that during speculation, then bad things could happen. So we can already use uncatchable memory to store our secrets. We don't have any taint tracking in hardware so far, but we might get that. There are patents for that. Compiler support, we can already do that. We have open source compilers. We implemented that in LLVM. Operating system support also works. We implemented that as a Linux kernel module. So except for taint tracking, we basically already have all the things we need to implement the solution. And if we look at that, what happens if we use this ConTExT Lite in the execution? We have this bounce check as before, and then we cannot access the secrets because they are in uncatchable memory. They're just not accessible, so we can also not leak them. Nothing happens here, but still, we can execute different instructions that are not depending on the secret loads. So this is nice. This gives us higher performance. And we can also compare that. It actually works. So we have like here an artificial example. We have this, the Oracle memory. We have a secret X. And we have some public value E. And we encode them in a Spectre-like covert channel. We have this like if speculate, so we only go speculatively into this if. And then we access two different memory locations, one depending on the secret and one depending on a public value. And if you don't have any protection, then we see for both values, the according page is stored, is cached, and we can retrieve both the secret and the public value. If we use the state-of-the-art mitigation with the elfence, and add the elfence after the if, then nothing is cached. So we also see this performance hit on the public value because it can't get into the cache. And if we do the same thing with ConTExT Lite, we're storing the secret in uncatchable memory and the public value not, we can see the public value can still be cached and it's fast, but only the secret value cannot be cached anymore and it's secure, and we only see performance hits on secrets. If we do that for real-life application, so we tried that on AES and I, it works on registers anyway, so we don't see any performance overhead. But for larger things like a VeraCrypt for hard disk encryption, we only see a slight performance overhead, especially for mounting, because it derives the AES keys. OpenSSH had a few more performance overheads for the crypto going on, like 5%. Also for a web server, it's totally feasible. So an Nginx is like 7.3% performance overhead. And this is with only our ConTExT Lite version with this uncatchable memory, which in a real implementation of ConTExT would not be uncatchable. So it would be a memory that's still cacheable, but it's just not accessible in transient execution. So you can also try that out. We open sourced everything we have, including the compiler batches and kernel module, to try that out yourself and see it's not that difficult. And now you might still say, but this new memory type no one is going to do that. Turns out, concurrently to our work, Intel released a white paper called A New Memory Type Against Speculative Side Channel Attacks. And they propose exactly this type of memory that works like that. And also concurrently, NVIDIA had a patent that also describes a memory type which is cacheable yet inaccessible by speculative instructions. So these are the things that are actually being worked on. So we hope that we can also see this solution soon in reality in commodity hardware. So for this talk, for a short talk, I skipped, of course, a lot of details, which you can find in a paper, like what you have to do in a compiler, how the taint tracking works, how we evaluated that, the tainting, untainting rules, context switches, a lot of details that you can find in the paper, which I just cannot fit in this talk here. But as a conclusion, ConTExT transfers the problem from an instruction-based problem to a data-based problem. So we only need to identify the secret data and not the instructions working with the data. That mitigates the root cause, the leakage, instead of just getting rid of the cover channel, as many other mitigations try to do. And then it's also applicable to all the variants of Spectre, because you remove the root cause, the leakage, to access to the secrets, and you don't care which variant of Spectre is used to try to leak the secrets. And all of that can be implemented fully backward compatible in commodity CPUs on x86. So these are things that look good for the future, that we can actually have a sane countermeasure against all these Spectre variants that we know so far and that we will still discover in the future. So thanks for being here and your attention. That concludes my talk.
Okay, a question from the audience. Last opportunity. Anyone? No one? Okay, I will start with one. So I know your group is very productive. I mean, in this line of research, I mean, super awesome. Like, I also read quite some papers from you guys. So, I mean, can you give us a little bit of hint about what would be the next thing you guys want to do, and yeah, give us some projections.
So the thing is, for most of the things we're working on, they're under embargo, so I can't say anything. So, but we are, of course, also working on mitigations for attacks. And yes, we live in exciting times. That's something I can say. And I'm pretty sure that there will be new things soon. But I can neither confirm nor deny that.
Cool. One question? Okay, cool.
Hi, yeah. I have a question about how you like which kind of data you protect exactly. So it might just be my own, misunderstanding, but I'm not quite clear on how, do you localize your protection in some very specific parts of the code? And in that case, what is your policy to decide, which branch conditions you want to protect as opposed to which ones you just want to leave alone for performance?
So do you mean that for ConTExT or for L-fences as we have now?
So I mean for ConTExT.
Okay. So for ConTExT, the developer has to identify what are the assets in the application. What are the things that you don't want an attacker to leak?
Okay, I understand. So you
don't care about the branches, because that's then fine. If you annotate the memory that stores the secret, then no matter what type of misspeculation, transient execution you have, you cannot access this asset there.
Okay, I get it. So you don't have an automated policy that could automatically retrofit those?
No. That would be really nice, and that's one of the biggest limitations. That still the developer has to know what the secrets are and correctly annotate them. And we all know annotating stuff is really complicated and error-prone, but it's still easier to do it like that, to find the secrets and annotate them, compared to what we have to do now, is to find all the branches, decide whether they could have something secret in them and then annotate these instructions there.
Okay, I didn't mean that as a critique, by the way. That was just
No,
curiosity. Thanks a lot.
Very interesting work from Cornell University. So I have a question about the performance overhead of ConTExT compared to LFANS. As you mentioned, that LFANS has like 50 to 70% overhead, and I assume that overhead is calculated by inserting LFANS to every branching instructions. Is that correct?
Yes, because the problem is you have some kind of code with branches in there.
Yeah.
And you never know whether it's used with secrets or without secrets.
But if you can human identify the secret, then you don't need to insert LFANS everywhere in your code. And if you only insert LFANS in around the secret, then how do you compare the performance overhead of ConTExT and LFANS?
But this is in most cases impossible. Think, for example, you're using the libc and you have a function in there like a memcopy function. And you will use the memcopy function for mostly non-secret data, but sometimes for secrets. So you have to add the LFANS there to ensure that if you use it with secret data, it doesn't leak there. So you need to do that in all the places with LFANSes, and you don't have to do that with ConTExT because you mark the data itself as being secret and not the code that can potentially leak data as being insecure.
Okay, thanks.
Hi, thank you for the talk. I'm a PhD student from Tsinghua University. And you mentioned that the developer should mark the secret. They think it should be protected. But there are still some secret data that is introduced from the compiler, such as the data pointer, the code pointer. Since there may be a lot of information leak, they want to do the information leak and do the further exploitation. So how do you think of this secret data that cannot be defined directly by the developers? Thank you.
Yes, that is a good question. And that boils down to this question, like, what do we define as being secret and what not? What is our threat model there? And of course, sometimes you would say, like, everything is secret because I'm working with my email client and I also consider my emails to be secret and my code layout to be secret, that I can't do any exploits. But then the question is this really necessary? If we look at the current attacks against Spectre attacks, I mean, they're not easy to mount, and they're also not fast. So you have data leakage of some, like, a few kilobytes per second in the best case. So the question is, would you really try to leak a lot of stuff with that or not? Because if I would be the attacker, then I would try to go for credentials. Like, I wouldn't attack an email client or something and steal the emails with Spectre, but go for the login credentials and then log into the email server and get the data like that. So yes, there might be things you want to protect, but they're not that of a high value for an attacker if an attacker is determined enough to use a Spectre exploit on your application. Then this information might not be the interesting information anyway for the attacker. But yes, sometimes this is a hard problem. So identifying what is a secret and correctly annotating that, this is a really hard problem, yeah.
Oh, thank you.
Okay, so if no questions from audience, then let's conclude this session. And thank you for attending this session at NDSS. And safe travel back home, and I hope to see you guys next year. Thank you.